Welcome back, citizens. This time in the very basic refrigeration set, we are going to have a look at compressors and why we use them and what different types there are. So to ask the question, why do we need a compressor? Well, in a refrigeration system, the compressor is often known as the heart of the system because it drives the refrigerant through the cycle, and its main purposes are compressing the refrigerant gas. It takes in low pressure, low temperature refrigerant vapor from the evaporator, and it compresses this vapor to a high pressure and a high temperature gas. Maintains the refrigerant flow around the system, and the compressor creates the pressure difference that is needed to circulate the refrigerant continuously between the evaporator, condenser, and expansion device. Now, without it, the refrigerant would not flow through the system, raising the refrigerant pressure and temperature. By raising the pressure of the refrigerant, its saturation temperature also rises. This allows the refrigerant to release heat in the surroundings, i.e. in the condenser, because it has a much higher Tsat temperature than the cooling medium circulating through the condenser, and thus condenses the gas back to a liquid. So let's have a look at the types of compressor that are available to us. In this case, reciprocating compressors. You can start off with a pot, the sort of compressor you would have in your fridge at home, and you could probably hold in your hand. And they go all the way up to this beast, which is a 12-cylinder Grasso, mainly used in large industrial equipment. So if we have a look here at this diagram, it shows a single reciprocating compressor. There you have the reed valves, one for the suction, one for the discharge. And the low pressure superheated gas comes in, and hopefully the high pressure, high temperature superheated gas goes out. Now, this is how reed valves work. As you can see here on the right, with the low pressure side, the valve opens on the downward stroke, allowing suction gas in, and then on the high pressure side, it opens on the upward stroke, allowing the high pressure gas to go out. So we have cold superheated gas coming in, and hopefully hot superheated gas coming out. So why is the gas now hot? Well, the reason that the gas is hot is because of compressive and frictional heat gain. If you've ever put your thumb over the end of a bicycle pump and pumped it, you'll notice that it gets very hot, and that is the reason: compressive and frictional heat gain. So here we have an illustration of a two-stage reciprocating pressure. We have low pressure superheated gas coming in, and high pressure, high temperature superheated gas coming out. These are used when the lift between the suction pressure and the discharge pressure is too great for a single cylinder, so therefore the suction gas from the high pressure cylinder is fed from the discharge of the low pressure cylinders. Now, scroll compressors, they are used in abundance now, especially in the air conditioning industry, and tend to replace reciprocating compressors for small units. We have a suction connection and the discharge connection. As you can see here from this representation, we have a fixed scroll and a rotating scroll, and the gas gets channeled from the suction and gets squished all the way down to the center, where it comes out as discharge gas. If we now look at screw compressors, as you can see is a fairly large example. They can range from about 50 kilowatts up to many megawatts of cooling. A short explanation of how they work. As you can see here on the left, the male and female rotors, a cross-sectional diagram showing what they look like meshed together, and end sectional diagram showing the male lobes and the female lobes. So here you can see one simulated operation where the cold refrigerant gas comes in at one end and the gas gets squashed along and comes out the high pressure, high temperature gas at the other end. Now we move on to my personal favourite, which is the centrifugal compressors. Here you can see a cutaway of a centrifugal compressor. We have the gas entry, known as the eye of the compressor, and we have the gas exit. Here you can see the impeller. There's the eye of the compressor, and there's where the gas gets discharged. The reason for the gas increase in pressure is because of centrifugal force. Here's another view. On the left you can see the impeller and the volute casing, which channels the gas away from the impeller, and on the right you can see a sectional diagram showing the volute casing, the impeller wheel, the impellers, the refrigerant intake and the refrigerant exhaust. You can of course get multi-stage compressors where the suction gas comes into the first wheel, it goes into the eye of the wheel and comes out the discharge. That discharge goes into the next wheel on the suction side and comes out a bit higher pressure, and it works its way along until you reach the pressure that you are looking for. We come along to turbo cores. These units are used in abundance nowadays in refrigeration, and they are oil free because they have magnetic bearings, and the regulation of the volume of gas is by the speed control and the IGV. So I hear you ask, what are pre-rotation vanes or IGVs? Inlet guide vanes. Well, the pre-rotation vanes are adjustable blades mounted at the inlet of a compressor. They are designed to impart a swirl or pre-rotation to the incoming gas before it reaches the impeller, and it regulates the volume of refrigerant flow through the compressor. So the PRV and the IGV are basically exactly the same thing. Here you can see an example of the pre-rotation vanes, or otherwise known as inlet guide vanes. You can clearly see the eye of the impeller, and you can see the blades that rotate and regulate the amount of gas flowing through the compressor. Two things to be cautious of with centrifugal compressors, that is surge and choke. Now surge is something that happens at low flow rates and the compressor discharge pressure is high. So in other words, it's out of its pumping curve. Now if the system pressure demand exceeds what the compressor can supply, flow reverses momentarily. This reversal causes violent oscillations of pressure and flow and is damaging to the machine. Now, choke, on the other hand, is a condition where the flow through the compressor reaches its maximum limit. The impeller inlet reaches a sonic velocity, Mach 1, and further flow increase is impossible. So basically, it's reached its limit. So that concludes this introductory lesson on compressors. And next time we're going to have a look at expansion devices.